Hello. In this lecture, we'll familiarize ourselves with vibrational spectroscopy. First of all, let's consider a diatomic molecule. Say, for example, hydrogen chloride, which is a stable covalent molecule. We are not going to examine how covalent bond is formed between hydrogen and chlorine atoms, but we will just look at the forces that are in action in such a molecule. There will be repulsion between the positively charged nuclei of hydrogen and chlorine, as well as the negative electron clouds of hydrogen and chlorine atom respectively. And there will also be attractive force between nucleus of hydrogen and electrons of chlorine and vice versa. The two atoms settle at a distance, at a mean internuclear distance, where all these forces are balanced and the energy of the system is a minimum. And let that distance be given by R equilibrium. That's the point where the two atoms settle and the energy of the system is minimum. If you try to push one of the atom closer to the other, or if you try to pull the atoms apart, the energy of the system, of course, increases. Okay, and that's what we've plotted here in this diagram. Now, if you compare the compression and extension of the bond to the behavior of a spring, you can apply Hooke's law and give an expression for restoring force F as minus K times R minus R equilibrium, where the term in the brackets indicates the displacement from the equilibrium position. And the energy of the system, potential energy, is of course given by half K R minus R equilibrium square. These two expressions you are familiar with from your mechanics course, and you can consider a vibrating diatomic molecule uh, with a simple harmonic oscillator model. Now, you just look at this equation. It is half K R minus R equilibrium square. K is the force constant, that's a constant, and the variable happens to be R minus R equilibrium. So if you are plotting E versus this quantity, E versus internuclear distance, then you get a parabola, and that is what we have shown in this figure. And the energy is minimum when R becomes equal to R equilibrium. When R becomes equal to R equilibrium, this term becomes 0. So the energy is 0 at R equilibrium, and for internuclear distances which are less than R equilibrium and greater than R equilibrium, the energy is of course higher. So as you push the atoms further close, or as you pull them further apart, the energy increases. Okay, and uh, when the atoms are brought further close to each other, or they are pulled farther apart, the degree of compression and extension is becoming greater, but the frequency with which the molecule vibrates, or the bond length changes, the vibrational frequency, that doesn't change. Now, if you consider this elastic bond like a spring, you can say that there is an intrinsic vibrational frequency with which the bond vibrates. And this oscillation frequency is given by this expression 1 by 2 pi root of K by mu, where mu is the reduced mass of the system. This equation also you might have learned when you learned the case of a spring in mechanics. Now if you are to convert this into centimeter inverse, you divide it by C and you get omega oscillation bar, and that is given by 1 by 2 pi c root of k by mu, that much centimeter inverse. Now, like any other form of molecular energy, vibrational energy is also quantized, and from solving Schrodinger equation for a simple harmonic oscillator, the energy that can be taken, the vibrational energy that can be taken, is quantized like this: V plus half H omega oscillation, where omega oscillation is the intrinsic vibrational frequency with which the bond oscillates. And here we can take values from 0, 1, 2, etc. And this is the expression for energy in joules. Now, if you are to convert the energy in joules to energy in centimeter inverse, you have to divide it by Hc. And then you get V plus half omega oscillation bar. Okay, this much centimeter inverse. So these are the only possible energies allowed for a simple harmonic oscillator. Now if you plug in the value V equal to 0, you get half H omega oscillation in joules or half omega bar oscillation in centimeter inverse. That's the ground state energy, or it's called 0 point energy. But here in the case of vibrational energy, you can see that 0 point energy is not 0. It is half H omega oscillation. Quite unlike rotational energy levels, where you saw that rotational energy, the ground state or rotational energy was 0. But in the case of vibrational energy, it is not so. 0 point energy is not 0. And the selection rule that applies here is delta V can change by plus or minus 1. So, considering this selection rule, if we look at the spectrum, transitions from 0 to 1 or 1 to 0 are possible, 1 to 2, 2 to 1 are possible, 0 to 2 or 2 to 0, such transitions are forbidden by the selection rule. Now, if you consider the energy difference between consecutive energy levels, suppose a transition happens from V plus 1 state to V state, the energy difference would be V plus 1 plus half omega oscillation bar minus V plus half omega oscillation bar, which would give me omega oscillation bar. Okay, so when a transition happens from an upper state V plus 1 to V, this much amount of energy is released. And for absorption to happen, this much amount of energy should be absorbed for a transition from V to V plus 1 to happen. Okay, now you can see that the difference in energy is independent of V, isn't it? So, for all the possible transitions, you can see that is from 0 to 1 or 1 to 2 or 2 to 3. Either ways, for all these transitions, the energy difference is pretty much the same. Why? Because there is no dependence on whatsoever on V. Since there is no dependence on V, it just means that from any higher state to the just lower state, this much amount of energy will be released on transition. Similarly, from any lower state to a state just above it, this much energy has to be absorbed. So here there is no relevance for whatever is the initial value of V. Whatever be the initial value of V, the transition happens by either releasing this much amount of energy or absorbing this much amount of energy. So that just means that all the energy levels are equally spaced. And what's the spacing? Spacing would be omega oscillation bar. So the ground state energy is half omega oscillation bar. So the upper state at a difference of omega oscillation bar would be located at 3 by 2 omega oscillation bar. The next state would be 5 by 2 omega oscillation bar, then 7 by 2, then 9 by 2, etc. All at differences of omega oscillation bar. Okay, and in the spectrum, you will just see a single line, because for any transition you get this energy released. So if there is a transition from 4 to 3, this much amount of energy is released. From 1 to 0, again the same amount of energy is released. So whatever be the transition, only this energy is observed in the spectrum. So the spectrum contains just a single line of energy, omega oscillation bar centimeter inverse. Thank you.